Hello, and welcome to episode 2 of Causal Foundations, a YouTube series in which I explore the philosophical and methodological foundations of causal inference in videos of approximately 10 minutes. In this series, I'll be modeling causation primarily through the use of causal graphs, and we've already seen examples of such graphs in the prior video. The technical term for them is directed acyclic graphs, or DAGs, and these are variables connected by arrows such that there are no cycles, so one cannot get from a variable back to itself by tracing a path of arrows all going in the same direction. The use of DAGs for causal inference is associated with people such as Judea Pearl and Spirites Gleamore and Shyness. Now, one reason why I decided to make this YouTube series is despite the fact that this work is several decades old, in my view, there's still no single streamlined entry point into the core concepts of causal inference. And I think this is a shame, because these concepts are not that difficult. Today I want to show that by taking a concept that would normally be intimidating and make causal graphs inaccessible, and show that it can be explained within 10 minutes. The concept I have in mind is deseparation, which, as we'll see, is a concept that links graphical structure to facts about probabilities. Now, in the previous video, we already started to see how probability and causation relate through the principle of the common cause, which once again says that if two variables x and y are correlated, then either x causes y causes x, or x and y share a common cause c, such that x and y are uncorrelated given c. So a good place to start will be to explicate what it means for x and y to be uncorrelated given c. To do so, we need the notion of conditional probability. This denotes the probability of b given a, and is equal to the probability of a and b divided by the probability of a. So if we have a die, given that the die is even, the probability that it's a 2 is 1 in 3. Using this notion, we can define conditional probabilistic independence. So x and y are independent conditional on c if the probability of x and y given c is equal to the probability of x given c times the probability of y given c. And this can be written as follows. So that expression indicates that x and y are probabilistically independent given c. Going back to the example in which the correlation between iPads and happiness is explained by income, the principle of the common cause indicates that the correlation between iPad and happiness will disappear conditional on income. So if we look at individuals all of the same income level, there will no longer be a correlation between iPad and happiness. Common cause structures are not the only ones for which x and z are independent given y. If we have a causal chain in which x causes y and y causes z, it will also be the case that x and z are independent given y. For example, if taking the vaccine lowers one's chance of getting COVID, and people without COVID can't transmit COVID, then conditional on having or not having COVID, vaccine will be independent of transmission. And here it helps to know that when x and z are independent given y, the probability of x given y and z is equal to the probability of x given y. And here philosophers will sometimes say that y screens off x from z, where the intuition is, if you know whether someone did or did not get COVID, further knowing whether they got the vaccine will provide no further information about their transmission probability. There's one more phenomenon I need to consider before characterizing the relationship between causation and probability. Specifically, independent causes of an effect may become probabilistically dependent conditional on their effect. So consider the variable for the number of subscribers on a YouTube channel, and imagine that there are two causes of a channel's being popular. Either it can have high-tech graphics, or it can have amazing content. And imagine that these causes are independent in the population. Given this causal structure, in which the effect is known as a collider, if we condition on the collider, it will induce a negative dependence between its causes. Now this is counterintuitive, but the intuition is as follows. Suppose you discover a YouTube channel which is very popular, and you see that it has terrible graphics. Well, now you know that its popularity can't be due to its good graphics, raising the probability that it has great content. We see that there's a fourth way to account for a probabilistic dependency other than the three listed by Reichenbach, namely through conditioning on a common effect. So given a correlation between iPads and happiness, it could be that both iPad owners and happy people are more likely to download cat pictures, and we just happen to be looking just at people who have downloaded many cat pictures. So we can develop an extended principle of the common cause, saying that any dependency needs to be explained in one of these four ways. A corollary of this is if two variables are not causally connected in any of these ways, then they are probabilistically independent. Deseparation gives a precise characterization of what it means for variables not to be causally connected. Let's make this all more precise. Consider variables x and y linked by a path, where a path is a set of connected arrows going in any direction. Because z2 is a common cause of x and y, we already know that x and y will be independent conditional on z2. Now, because z2 blocks the transmission of probabilistic dependence along this path, we say that x and y are deseparated given z2 along this path. We could also deseparate x from y by conditioning on z3, or z1 for that matter. Now suppose there's this additional path. Notice that z4 is a collider. As long as one does not condition on z4, or any effect of z4, x and y will be deseparated along that path. So x and y will be deseparated along a path if it either contains a common cause or chain where one does condition on it, or a collider where one does not. Finally, x and y will be deseparated full stop if they are deseparated along all paths between them. When variable z deseparates x from y, it's denoted as follows. So this says x and y are deseparated by z2. And you've probably noticed that the symbol over here is the same as that for probabilistic independence, but with a G for graphical instead of a P for probabilistic. And the reason for this is something called the causal Markov condition, which is a generalization of the principle of the common cause. It states that if x and y are deseparated by z in the true graph, then x and y will be independent conditional on z in the probability distribution. And what this means is we can take any graph, look at the deseparation facts, and learn which variables must be conditionally independent if that graph is the true one. Finally, when two variables are not deseparated, we say they're deconnected. So now that you have the basic concepts, let's practice a bit. So here we have a causal model, and we want to know whether x and y are deseparated. Well, first of all, because all paths from x to y go through z1, and z1 is a collider along all paths, we already know that x and y are deseparated. Additionally, they're going to remain deseparated conditional on any set that does not include z1. To make things more interesting, let's imagine we do condition on z1. So, because that's a collider, it will open up various new deconnecting paths. Several of them will go via z2, and we can get rid of those by conditioning on z2. This leaves open a path via u, which we can also condition on. So, conditioning on z1, z2, and u deseparates x from y. Now let's suppose that we can't condition on u because it's unobserved. So now we have this path via z3, which we can eliminate by conditioning on z3, but that opens up another path because z3 is a collider, so we also need to condition on z2. Finally, if we condition on all of those variables plus u, that is also a deseparating set. That's it for today. I'll conclude by putting up Pearl's definition of deseparation. Now, this doesn't say anything that I haven't already clarified, but I think if you came across this in a textbook, it could be very intimidating, and is the type of thing that bars people from further exploring causal inference. So I hope to have convinced you today that the underlying concepts here are not very difficult, and with just a bit of practice, you could also become an expert in reading off deseparation from a graph. Thank you for listening. Here are some topics I'll be covering in future videos. What topics would you like to hear about?